and then we're going to dive in and start talking about polynomials. Okay? Yo.
What are the syllabuses do?
Sunday at midnight on the thingamajigger, the OneNote.
Oh, online?
Yep.
Can I print in a hard copy right now?
You can take a picture of it right now and then drop it into your OneNote. So that's perfectly fine if you did a hard copy. Just take a picture of it and drop it into OneNote.
You want an extra mask?
No, thank you.
I like you found this one. It's really
All right. So looking at this paper that we worked on yesterday, the first questions were factoring questions. Reminder, there are 3 basic ways to factor something. So they all depend on either the number of terms or the leading coefficient. In the case of number 1, since the leading coefficient is 1, all we need to do is find 2 things that multiply -21 and then add to give us -5. The things that multiply to give me -21 are these 4 things. Unfortunately, none of them add to give -5, so we'd say that this is not factorable. You could have also determined that by showing that b squared minus 4ac is not a perfect square. Again, remember, perfect squares are things like 1, 4, 9, 16, 25, things that is like a number squared. Number 2 is just 2 terms. If it's a 2-term thing where that's still quadratic, maybe it's a difference of 2 squares. So the difference of 2 squares factoring pattern was this. So I can rewrite x squared as something squared. X squared is just x squared. And 81 I can write as something squared. That would be 9 squared. So I can use that difference of 2 squares factoring pattern to write this as x minus 9 times x plus 9. Number 3, the leading coefficient isn't 1. So to factor this, I'd have to do the long factoring method. So I'd start by finding the 2 numbers that multiply to give me the first times the last, and then add to give me the middle. So multiplies to give me -90 and adds to give me +1 is 10 and -9. Unfortunately, those don't go straight through to give me my answer. So instead of the 1x in the middle, I'm going to write it as 10x minus 9x. Or you could have written it as 9x or -9x plus 10x. That would be fine. And then we'll take a greatest common factor from the first term. That's a 2x. After I take the 2x out of 6x squared, that's a 3x. And if I take 2x out of 10x, that's 5. Similarly, in the second group, I can take out a -3. So that becomes 3x plus 5. And then if I look at each of these, they both have a 3x plus 5 in common. That leaves me with just the 2x minus 3. And there's my factored result. Four, very similar to the previous problem. So I need to find 2 numbers that multiply to give me 25 times 13. I think that's 325. And then add to give me -20. Now 325 is a big number. It has kind of a lot of factors in it. Not that many factors, but enough to where you try this and maybe you can find one, maybe you can't. I've been looking at it for a while. I'm not really sure. Maybe it's not factorable. Let's check it by doing the b squared minus 4ac piece. That comes out to be -900, which is not a perfect square. So this is not factorable. You could have also done that by running through all the factors of 325 and check to see that none of them added to give you negative 20, but that's a little bit time consuming. I'm going to usually look at it for a couple of seconds, and if I don't see the two numbers right away, I'm going to check to see if it's factorable or not, because I don't want to spend a whole bunch of time going through checking a whole bunch of things only to find out it didn't actually work. Or maybe I find out that it does work, and then it's like, okay, better keep checking. You know what I mean? Last one, also a potential difference of two squares candidate. So 4x squared I can rewrite as 2x squared. And 1 I can rewrite as 1 squared. So this just becomes 2x minus 1, 2x plus 1. So just like number 2, except the leading coefficient wasn't 1. But I wasn't concerned about the leading coefficient. It was just that I had two terms there. Was my indicator that maybe that would be a good candidate for a difference of two squares. Okay, on to the second page. Problems. Remember that all quadratics are solvable, so every single one of these should have an answer. We would have talked about 3 major techniques for solving. So the 3 major techniques we would have used are factoring, solving directly, and then the quadratic formula. So solve or factor by solving has the drawback that not everything is factorable. So if you can't factor, you can't use that technique. Solving directly has the drawback that if you have both x squareds and x's, you can't use that technique. But the quadratic formula, you can always use. Maybe it's a little bit longer than those other 2 techniques, but it'll always work. So number 6. I look at this and I have the leading coefficient is 1, so maybe I can factor this quickly in my head, which would be a little bit faster than using the quadratic formula. So I'm going to look for 2 numbers that multiply to give me 24 and add to give me 10. Those 2 numbers are 6 and 4. So because the leading coefficient is 1, I can go straight to the factored form. And then since it's factored, I can use the zero product property to solve this by setting each factor equal to 0, and then solve each factor separately to give my answers of negative 6 and negative 4, which was probably a little quicker than using the quadratic formula, but it still would have worked. So if you use the quadratic formula, that's still super fine, definitely okay. Number 7 has just x squareds, but no x's, so this is a good candidate to solve directly. That's what I would do here. So to do that, I'm going to subtract 9 from both sides, and then divide both sides by 4. And then we'll square root both sides. Remember, when we square root both sides of an equation, though, that creates a plus or minus. And when we square root a fraction, to do that, we just take the square root of the top and the square root of the bottom separately. The square root of a negative creates an I, so the square root of negative 9 is just square root of 9 and with an I after it. And the square root of 4 is just 2. So there's my answer there. Again, you could have used the quadratic formula there. That would have been totally cool. It wouldn't have been much more difficult than what we just did there. You might have had a little bit of reducing to do or something, but not too bad. 8. Again, this is one that might possibly be able to be factored, but notice since the leading coefficient isn't 1, to factor it, I'd have to use that long method, which probably is not any faster than just using the quadratic formula from jump, which is what I would do in this case. So I'm going to do this using the quadratic formula because I don't think it's going to be any slower than trying to factor this. In general, if I have to use that full factoring method, I would rather just use the quadratic formula if I'm solving. You know what I mean, guys? Because that hunt for the 2 numbers that like multiply to give us and add to give us is sometimes kind of irritating. So negative of a negative 27 is positive 27. 27 squared minus 4 times 10 times negative 28 square rooted is 20. So since 43 is a whole number, I definitely do the plus or minusing. So 27 plus 43, 2. And 27 minus 43 over 20, 18 over 20, or negative 4/5. if you turn those into decimals, that would be totally okay also. I think I remember walking by and seeing people write those as decimals. Totally cool. I prefer fractions personally because it's one less thing to put in my calculator or whatever, but since those are both terminating fractions, NBD. So far, so good? Okay. Next one, number 9. I noticed the leading coefficient is 1, so maybe if I can factor this, it'll be quick. So let's check. 2 numbers. No, that don't work. Well, better use the quadratic formula then. The next one, so negative of negative 4 is 4. Negative 4 squared is 16. Minus 54 is negative 36. The square root of negative 36, because it's a negative, so that's my figure there. And the last one, again, leading coefficient is 1. So let's check to see if we can factor that. So multiplies to give me 1, adds to give me negative 3. No, that doesn't hunt. So quadratic formula time it is. Negative 3 squared is 9, minus 4 times 1 is negative, or it comes out to be 5. And the square root of 5 can't be simplified, so this is as good as we can do. So that's what we'll represent our final answer as. I saw some of us gave decimals on this. I would prefer in this problem to leave it the way it is. If you're taking a standardized test, it's unlikely they would represent the choices with a decimal there. They would most likely represent it with a exact answer with the square root still in it. Depending on my instructions, I might mark down if you gave me a decimal if I asked for exact answers. So if you have to do rounding, and I ask for exact, that's not following directions, I would make a deduction there. But if I didn't indicate how I wanted my answer to look, I obviously can't be picky about that. Just so you know why I'm being picky about the decimal thing. Most often on a standardized test, they would give you an answer that looked like that. So hopefully you can still generate those kind of answers, right? And not just rely on having the decimal. Okay, questions about any of these? We buzzed through those kind of quickly, but they should have largely been review. The reason I chose these problems as review problems is when we're talking about polynomials. That's what we're going to start talking about. And when we start factoring and solving polynomials, the idea is to take that big polynomial and break it down into smaller pieces that are easier to deal with. Amongst those smaller pieces that we'll end up with are often quadratic pieces that we can use these same quadratic factoring and solving techniques on. So these things will come back into play when we start factoring and solving polynomials later on in this chapter. So I wanted to make sure that we had at least taken a little bit of time and reviewed these things. I think first semester, this was one of the topics I thought we spent a lot of time with and really tried to make sure we got fairly comfortable with and fairly good at. So, because I knew that this is going to come back several times in second semester. So I wanted to make sure that we were good there and at least spent a little bit of time here at the beginning of the year doing some work on these concepts. All right, so today we're going to start talking about polynomials. So our agenda today, when we talk about polynomials, we need to do some polynomial vocab. We're going to talk about operations on polynomials, so how we add, subtract, multiply, divide them, and then talk about one other special topic called synthetic substitution. Students that had me first semester, we had covered all these. These are like the last couple of things we covered before the end of the semester. I don't think if you came from Miss Morgan's class that you guys got quite that far. So this would be new to you. Fortunately, none of these beginning topics are too terribly complicated. So that's not a bad deal. I think basically by next class period, everybody will be kind of back at the same spot. So you were not too far behind and the other class wasn't too far ahead. We're just going to kind of meet there at the same spot till we can get everybody so that we're all seeing new things. Okie doke. Okay. So we're just going to start with some vocab here. So we're going to do a bunch of definitions and some vocab stuff, and then we'll dive into actually doing some like actual math things. But before we can do the math, we need to have a language about what it is we're talking about and how to communicate these ideas with one another. So we'll start with a definition of what a polynomial is. So a polynomial is the sum or difference of a finite number of monomials. Well, gee, Mr. Kulik, that's a great definition if I knew what the heck a monomial was. Well, guess what's the next thing up then? Better define what a monomial is, right? Okay. So a monomial is the product of a finite amount of real numbers and variables. So let's just, again, both of these definitions, while nice and tight, aren't really like practically useful in terms of what the heck am I conceptualizing a monomial or polynomial as. So let's do some examples just to kind of get us a better working definition of what we mean by that. So we'll start with some monomials, and we're just going to write down some things and decide if it meets the definition or not. Then we'll kind of reword this definition into a little bit, something that's a little bit easier, more practical for us to use on a day-to-day basis. So 7x squared, is that a monomial? You betcha, because we could write it as 7 times x, right? That's the product of a finite number of real numbers and a finite number of variables. That's a monomial. So you might be thinking, well, what's something that's not a monomial then? About 5x to the 1/3. Not a monomial, right? The reason is that exponent being a 1/3, that we can't represent as a single variable. Yes, sir?
The polynomial is product of a finite what?
Amount.
Oh.
Yep. Okay. So one thing we can say straight away then is that the exponent on the variable must be a whole number, right? Okay. How about 10x to the negative 3? Is that a monomial? No. The reason is that that would be the negative exponent indicates division, which is not multiplication. So in addition to having the exponent need to be a whole number, it must be a non-negative whole number. So negative exponents on our variables are out. That can't be a monomial. How about 8 square root of x? Is that a monomial? Nope. Why not? Well, the square root isn't multiplication, right? So the only operation that we can have for a monomial is multiplication. A square root is definitely not that, so that's not a monomial. What else could we say? 7 over x. Nope. Good. Why not? It's division. But what if we had x over 7? That is a monomial because it's really just a real number, 1/7 times x. So if the number part is in the denominator, that's okay. If the variable is in the denominator, that's bad. We have a little bit better conception of what we mean by a monomial now after running through some practical examples. So again, the number doesn't matter if it's in the numerator or denominator, doesn't matter the exponent on the number, doesn't matter if there's a square root over the number, that part doesn't matter. The variable must be in the exponent, must be a non-negative whole number. Can't have anything else over the variable, right? No radicals or anything else. Everybody cool? Okay, so then a polynomial is just a bunch of monomials linked together. So let's look at this guy and decide if this is a polynomial or not. Again, the way we do this is we look piece by piece. So 7x to the fifth, is that a monomial? 10x y to the third, is that a monomial? Yes, right? Again, the exponents on the variables are both non-negative whole numbers. And on the 10 over square root of x, is that a monomial? Yes. Again, the variable, the exponent is a non-negative whole number because what is the exponent there? Really just 1, right? So because they're all monomials, that thing is a polynomial. Everybody's good with that?
Like that, no square root.
On the variable. If the square root is just over the number part, that's okay. So like here, notice that the square root was over the variable. That's why that one's an issue. But if the square root was just over the 8, that would have been fine. Is that okay? Okay. Let's do one more. So let's say we have 6x squared y minus 7x to the third y plus 6x squared y to the 1/2. Again, is the first piece a monomial? Yes. The second one? The third one? No. So this thing is not a polynomial, even though some parts of it were monomials. If all of it isn't monomial, then it can't be a polynomial.
Why is the third thingy not a monomial? That's a zigzag. Oh.
The exponent is not a whole number. Everybody feel okay on this? Being able to just identify what is or isn't? Okay. So now we need, now that we've established what a polynomial is or isn't, we need to get some kind of a language to describe these different parts of a polynomial, or these different attributes. The first thing that we're going to define is the degree So the degree of a polynomial is equal to the largest degree of its monomial terms. Again, Mr. Kulik, you did this last time. That's great, but how the heck do I find the degree of a monomial then? Well, let's define how to do that then, since the polynomial just comes down to the monomial part. So the degree of a monomial is equal to the sum of the exponents on its variables. So let's do some examples here to just kind of get familiar or comfortable with these two definitions. So 7x to the third. This is a monomial, right? So its degree is 3. Just the sum of the exponents from the variables, right? Since there's just one exponent, it's just that exponent. Two x squared y to the fourth, also a monomial. What's its degree? 6. 2 plus 4, right? The exponent on the x's plus the exponent on the y's. Is 8 a monomial? It is. Meets the definition. It's the product of numbers and variables, right? We just didn't multiply any variables. That's okay. So this is a monomial. What's its degree going to be then? Not 1, because what's the exponent on the variable? Is there a variable? No, so its exponent would be 0. As opposed to if you had 8x, that has degree 1, because the exponent on the x is 1 in that case. Everybody feel okay about using the degree on monomials? So to do a polynomial, so let's say we have this polynomial. What we'll do is we'll just go monomial by monomial and figure out the degrees. And whichever one is the biggest, that's the degree for the polynomial. So this first monomial is degree 3. The second one is degree 2. We have degree 4. And then we have degree 5. So for the polynomial, we are degree 5. Check. Yes, 6x squared y. That's what you're asking? If that's an exponent of 2? Yeah. Did it get messy? Sorry. I apologize. But we're okay doing that? Again, pretty easy. All we're really doing is counting and applying a definition, right? Yes?
How do you find it?
For the polynomial? So the degree for the polynomial is the largest of its terms. That's okay. So for a monomial, it's the sum of the exponents on the variables for a monomial. For the polynomial, it's just the biggest monomial degree.
So for that one, for E, the degree of monomial before D?
For E is a polynomial, right? Because we have a bunch of monomials added together.
Yeah, no.
If those were addition and subtraction symbols, if they were multiplication symbols, then yes. Because it would be a monomial then, because it would just all be multiplied together. But since they're added or subtracted, it's a poly. Is that good?
Yeah.
Okay. Everybody happy with this idea? Super important concept. It's really simple, but we'll use it a lot. There's a lot of things that we do that depend on degree later on, so it's really important that we're able to find the degree of a polynomial. But it's not complicated, right? You're just kind of using your eyes. So that's nice. Next piece is the leading coefficient. So the leading coefficient is just the coefficient on the monomial with the largest degree. So let's say we have the polynomial 7x squared y minus 10x squared plus 18 minus 7x to the fifth. To figure out the leading coefficient, we need to look at the degrees. So we have a degree 3 term, a degree 2 term, a degree 0 term, and a degree 5 term. So the leading coefficient is going to be -7, since it's the coefficient on the term with the largest degree. Everybody happy with that? Again, super easy concept. We'll use that term a lot, so it's nice that we have a piece of vocabulary that's pretty easy. In fact, we've used leading coefficient a bunch of times before already when we talked about quadratics, right? We just never formalized it.
Also, leading coefficient would be like the number of the greatest degree.
Yep. So the constant term is just the monomial term that has no variable. So for this one, what would the constant term be? -10. Okay. What about if we did this one? What would the constant term be here? It would be 0. Yeah, good. So remember, you can always add like a +0 on at the end. So if there was no constant term written, you can always write a +0 at the end to make the constant term 0. Very good. We feel okay on that? Again, pretty easy concept. All right. Last pieces of vocabulary, we want to talk about naming polynomials. So there's two different ways we typically name polynomials. One way is naming them by degree. So if the degree is 0, we call that a constant polynomial. If its degree is 1, we call that a linear polynomial. Degree is 2, that's a quadratic polynomial. Degree 3 is a cubic polynomial. Degree 4 is called a quartic polynomial. Any degrees bigger than 4, we're just going to call that degree whatever polynomial. There are special names for them, but they're used so infrequently that it's not even worth kind of listing them. For example, like I think degree 5 is quintic. Like the word quint is, those of you that watch those TLC shows about people that have like 1 million babies all at once, I think 5 babies is quints. I think it's the same prefix there. But again, those bigger degree polynomial names are used so infrequently that it's not worth our time. You know what I mean? We have bigger fish to fry than remembering that prefix for something with like degree 9 or something. Okay. Quartic, yep, like quarter. So degree 4, just like 4 quarters in a dollar, or 4 quarts in a gallon, or whatever. You know what I mean? So the other way we name polynomials is by the number of terms. So how many monomials you have. So one term, well, that's just a monomial. 2 terms is a binomial. 3 terms is a trinomial. And then bigger than 3 terms, we just say it's a whatever number of terms polynomial. So typically, again, there are special names for those, but they're used so infrequently that like it's not worth, like I don't think I know even the name for a 4-term polynomial off the top of my head. I'd probably have to go look it up, which tells you that it's used so infrequently that it's not even, you know what I mean? Like you just want to worry about the stuff that's common. Okay, so let's just do an example. So this polynomial 3x cubed minus 4x squared plus 1. The degree here is 3, so this is cubic. And the number of terms is also 3, so it's a trinomial. So we could call this a cubic trinomial. Everybody okay with that idea? I think that's it for vocab. If I think about anything else that I omitted, we can always add it in later, but I think those are the big ones. We're going to move on now and start talking about operations with polynomials. So when we talk about operations, I'm talking about like addition, subtraction, multiplication, and division. Okay. And these are all relatively straightforward, or are things that are pretty similar to things we've already done. So